I'm sure you all went through and did the starter question. You filled this stuff out. Whoa, listen up. Thank you. There we go. Okay, if the equation has one squared variable, then it's what? Parabola. If it has two squared variables, there are three choices. Okay, we have to look at it. If it has two squared variables, if they have the same sign and the same coefficient, exact same sign and same coefficient, what is it? Circle. It's a circle. Same sign and different coefficients. So they're both positive or both negative, but they're not the same number. That's an ellipse. And if they just have different signs, doesn't matter what the numbers are, doesn't matter what the coefficients are, if they have different signs, then it's a hyperbola. Okay? So this section is on ellipses, and just like all the other ones, I said we'd start from a definition. And I'm going to do a quick demonstration of this. That's why I had to run back to the office there. It says an ellipse is the set of points on a plane, the sum of whose distances from two fixed points is constant. I'll say that again. Set of points on a plane whose distance from two fixed points is constant. Okay, the two fixed points are called foci. Okay. Now I suppose you could say foci if you want. It's foci, but there you go. Okay? Now you can look in the book and they've got some pictures and demonstrations and that sort of thing. Okay, I'm going to show you what this looks like up here on the board. Okay, so there's one focus, and there's another focus. So rather than saying they're both F, we're going to call this F1, and we're going to call this one F2. Okay, and those are the fixed points. Okay, and then Samantha, can you come up here, please? Yes. Thank you. Alex, can you come up here, please? Okay, you're going to be focus 1. Okay. Okay, and you're going to be focus 2. All right, so they're going to take those and they're going to hold them right on top of there. So just hold them right on the focus there. Okay, this string, that's the, turn it over so the string is closer. There you go. Oh. Beautiful, like this.
Like a bionicle?
I think it is from a bionicle. It's either that or from Legos somewhere. Okay, so those are two fixed points. They're not going to move. So they're going to move their hands really close here, and they're going to kind of hold it like this. Excellent. Okay, so those are fixed. They're not going anywhere. This is a set distance. So this string is the same length. It's not going to change. So if I move over here, the distance from Samantha's focus to that point and Alex's focus to that point, if you add them up, they're always going to be the same. So if I move here, the string hasn't changed length, okay, but I've got that right there. Does that make sense? Two set points and a fixed distance in total. Good there? Okay, so I'm going to take this and I'm going to put this here. I'm going to go like that. Go ahead and take those off. Okay, what does that look like? Kind of looks like a half circle. Okay, go ahead and put them back. Let me do the top here. That's good. Okay, what does it look like now? Still looks like a circle? Okay. Yeah, please give me the right answer.
It does look like a circle.
Okay. It does kind of. Okay, go ahead and line them up here.
You have no idea how strenuous this is.
Yeah, you guys are not cooperating. Okay. What happened to the foci? What did I do with them? Moved them further apart. What does it look like now? Okay, thank you. Finally the right answer. What would happen if I moved them even further apart? Get skinnier and skinnier. Would there be a limit to how far I could move them apart?
Then it would just be a line.
If you were to make it closer, would they go skinnier?
Let's see what happens if I move them closer together. Okay. So this was, okay, now does everybody agree this is an oval, it's not a circle? Okay, this is an ellipse. Okay? It's a little bit squished. Okay? All right, everybody will agree this is definitely an ellipse.
What's your first drawing?
Tell you what, all right, I'm gonna prove a point here. Let's do that. There's F1 and there's F2. Okay, go ahead. Okay. What?
The best at math, but when what? Not always
Harder than it looks, right?
That's a legit circle.
That looks more like a circle than the last one, right? Okay, so would everybody agree that in general, you guys are good, thank you very much.
Oh, I get it. As they get closer to becoming one centered point.
Say that again?
The closer they get, the more like a circle they look because they're closer to being just one point.
Okay, the closer they get, the closer those two foci get, the closer the ellipse gets to a circle. The further apart they get, the more narrow it gets. There is a limit, okay? There's the limit to how far apart they could get is how long my string is, okay? But if we used a different definition, different length of string, we might be able to make a bigger ellipse. So the further apart they get, the more elongated it gets, okay? And we could have done this too. We could have done a focus here and a focus here. Oops. What would that have done? Yeah, that would have made it shaped like this, okay? Everybody good there? Okay, that's the definition. That's how the definition produces it. Now, we could go through and we could come up with the equations and all that sort of stuff, but we're just going to go with this, okay? All right, let's see. So we know from previous sections that ellipses have two squared variables that have the same sign but different coefficients. Okay, now, ellipses are a lot like circles. In fact, we could go back and treat circles like we will an ellipse. Okay, so for example, here's a circle, okay, and here's a parabola. Okay, ellipses have some of the same important parts that a circle has. It has a center, okay, but it has foci, and then we have what are called vertices, major axis, and minor axis. Okay. And all of them can be figured out where it is, what's the center, where are the foci, where are the vertices, all that sort of stuff, just by having it in a nice graph-friendly form. Okay, and this is the graph-friendly form right here. Okay, so this guy right here. So if we can make a perfect square with x, with a number underneath it, a perfect square of y with a number underneath it, and we make this other side equal to 1, okay, then it's an ellipse that's centered at, guess where this would be centered? 0, 0. Okay? From the center, we go A units in the x direction and B units in the y direction. So take a look here. The reason we go A units in the x direction is because A is underneath the x. The reason we go B units in the y direction is because B is underneath the y. Okay? The major axis is determined by whichever is bigger or larger or greater or whatever word you want to use out of A and B. The foci are always located on the major axis. And just a quick reminder, where are the foci? On all conic sections, they're always inside the curved part. So you'll notice on the examples on the board, the foci are always on the inside. It's curving around like this. Okay? If we kind of stretched it a little bit, with a circle, the foci is right at the center. Everything points right directly toward the center. Okay? The foci are C units from the center on the major axis. And we use this formula right here to find out what C is. So when we were dealing with parabolas, all we worried about was what's A? A is the distance from the center to, the vertex to the focus and the vertex to the directrix, and it also helps us figure out the endpoints of the lattice rectum. Okay, when we're dealing with an ellipse, we've got a few more things to worry about. We've got to go A units in the x direction, B units in the y direction, and then we've also got to figure out where's the focus. It's C units from the center on the major axis, and we find it using this formula right here. Okay, does that look at all familiar? What does it look like? It's kind of like the Pythagorean theorem, except for it has a minus rather than a plus. So it's like the Pythagorean theorem, but it's got a minus rather than a plus. And the way I like to tell people to think of this, and this is going to be important when we deal with hyperbolas, is it's the big one minus the little one. So the big one squared minus the little one squared. So whichever one is bigger out of the two of these, take the big one, subtract the small one, and that will help you figure out what C is. Okay, here's the reason we have to take the big one and subtract the small one. Okay, the big one is going to be this length right here that I'm showing you on the board. Okay, we've got to be smaller than that, so we're inside the curved part of this conic section. We've got to be inside the ellipse. So we take whichever one's bigger, subtract whichever one's smaller. Okay, and please don't forget this. A squared is always the big one. Okay, now if you look in the textbook, textbooks normally teach this differently than I do. They show you lots of different forms and they make a big deal of, oh, A's always got to be the one underneath the X or the Y or something like that. Okay, if you'll always think of A squared as the big one, you'll be in better shape. And you'll notice that these are both positive, so it doesn't matter if I write the y squared first or the x squared first. Just look underneath the x, that's the one that goes in the x direction. Whichever one's underneath the y, that's the one that goes in the y direction. And which one is A? A is the big one, okay? So on this problem right here, what's A? Which one's A? 25. A squared is 25, okay? So where is the center for this ellipse? Okay, hold on. Center. Center. 0, 0. Center is at 0, 0. We don't have x minus h quantity squared and y minus k quantity squared. So the center is at the origin. So we're right here. 0, 0. Now, to draw this ellipse, we go further in the x or the y direction to make it elongated. On this particular one, which one's bigger? 25 is. It's bigger in the x direction than it is in the y direction. So it's going to look like one of these that I've got on the board over here. Okay? So how far do I go in the x direction? I go 5. Whatever this number is, whatever's underneath the x, take the square root of that. That's how far you go in the x direction. So I'm going to go, the square root of 25 is 5. 1, 2, 3, 4, 5. So we're right here. I go that much in each direction. How far do I go in the y direction? I go 3 in each y direction. 1, 2, 3. 1, 2, 3. Everybody watching? Okay, you don't have to do this, but I like to do this. In the long run, I think this is a good idea. A lot of people have trouble drawing these so that they look nice. So here's what I like to do. I like to draw a little box around this, just a little dotted box. And that kind of helps me get this right, because the ellipse is always, it's kind of curving around from here, like this, and like this. So it kind of helps me run along here and hit each one of them. Okay, mine looks a bit like a potato. Hopefully yours turned out better. Good there? Okay, what's this point right here called? That's called the center. Okay, the center is at 0, 0. Okay, these points are all vertices. There are 4 vertices. So there's a vertex here, a vertex here, a vertex here, and a vertex here. Those points are not hard to find. We went over 5, so this is 5, 0. We went back 5, so this is negative 5, 0. We went up 3, so this is 0, 3, and we went down 3, so this is 0, negative 3. Okay? Those are the vertices. Okay, now you may occasionally find a book or a teacher says, hey, the vertices are only on the long one. Okay, I don't care. Call them all vertices. Okay, they're all important points for you to graph. Everybody good there? Okay, are we done with this? Have we graphed all the important parts of this conic section? We haven't. Okay, the last thing we need to find is we need to find the foci. Remember, the foci were part of the definition. Just like the focus on a parabola was part of the definition, we want to graph that. They are always inside the curved part of the conic section. So they're going to be inside here somewhere. They are always on the major axis. This is the major axis right here. That right there is the major axis. Okay, what do we call this then? That would be the minor axis. Okay, so listen carefully, please. How long is the major axis? 10. 5 here, 5 there, 10 altogether. The major axis is 10 units long. How long is the minor axis? The minor axis is 6 units long. Okay, now I'm going to throw another couple words out at you. Okay, does everybody know what a semicircle is? What is a semicircle? Half a circle. What's the semi-major axis? Half the major axis. Okay, it's a fancy word for how long is this right here? Okay, what is A? Would be another way to think of it. A on this one, or the semi-major axis, is 5. Semi-minor axis is 3. Okay, is that okay? So major axis is always the long one. That one goes with the A. Minor axis is the short one. Okay, that goes with the B. Now, the foci are always on the major axis. They're always on the long axis. You'll notice these examples on the board. This is the long axis. This would be the short axis. Major, minor. Foci are on the major. This would be the major axis here. The foci are on the major one. Okay? So here's how we figure it out. Again, it's the big one minus the little one. So we're going to do 25 minus 9 equals c squared. 16 equals c squared. So c equals 4. So from the center, I go 4 units in each direction on the major axis. So that's one focus, and that's another focus. And labeling these are really easy on this particular one. This one's 4, 0, and this one's negative 4, 0. Okay, are there any questions? Easy enough? Okay, does the major axis always run horizontally? Nope, they don't. Okay, what would we have to change to make it run vertically? Okay, make the bigger number underneath the y. Okay, so all right, let's take a look at the next one. Okay, so this one is a little bit different. Okay, this is still an ellipse. Where's the center? 1, negative 1. Okay, again, find the x. Opposite of that is 1. Find the y. Opposite of that is negative 1. Okay, again, don't mess that up. Okay, especially in the book, they like to switch orders. Okay, look at the number underneath the x term. So if the center is at 1, negative 1, we're right here. Look at the number underneath the x. What is it? 9. What's the square root of 9? 3. So we're going to go 3 units in the x direction. So if this is the center, I'm going to go 1, 2, 3 right there. 1, 2, 3 right here. Look at the number underneath the y. Square root of that is 5. So in the y direction, I'm going to go 5 units. 1, 2, 3, 4, 5. They may have done it yesterday. Did they do it yesterday in the morning and the afternoon?
They did it during third period.
Did they? I don't know. There's not much we can do about it. Okay? So I'm going to draw this little box around here. That'll help me draw the ellipse. Help make it look right. Okay, that, mine's more like Humpty Dumpty. Okay, but does that look okay? Okay, I really don't appreciate that.
Power ad.
Okay.
Power ad.
Okay, the center is at 1, negative 1, and then we'll label the vertices. Okay, again, because all we're doing is we're going in the x direction. I went forward 3, so this is going to be 4, negative 1. I went back 3, so this is going to be negative 2, negative 1. I went up 5. And I went down 5. So this is going to put me at Well, the x coordinates are the same. I go up 5, that's going to put me at 4, 1 comma 4. If I go down 5, that's going to put me at 1 comma negative 6. Everybody okay there? What's that? Because we were at negative 1 to start with, and we went up 5 in the y direction. Questions there? I mean, on a simple one like this, you can probably count. Questions? Okay, how long is the major axis? 10 units long, just like the other one. The difference between this shape and this shape right here is this one's oriented horizontally, this one's oriented vertically. Okay? Other than that, that's pretty much the only difference. Same shape, we've just kind of spun it a little bit. Okay, are we done labeling things here? What else do we need? We're listening to this. What else do we need if we're going to get this labeled correctly? Foci. Okay? So, we're going to take, now do I do 9 minus 25?
25.
Big one. A is always the big one. It's a squared minus b squared equals c squared. So it's always the big one. So 25 minus 9. We're going to get the same thing. We're going to get c equals 4. So I'm going to go up 4. That's going to put me with a focus at 1 comma 3. And I'm going to go down 4. That's going to put me with a focus at 1 comma negative 5. Okay? Let me blow that up just a little bit. If yours is labeled like that, if this were a test question, you'd get that right. Any questions? Yeah. This 3? No, because this is at 4 right here. Okay? We went from negative 1 up 4. Negative 1 plus 4 would be 3. If we go 1, 2, 3, 4, that puts us right here. If we go 1, 2, 3, 4, 5, that puts us right here. And you can count. That's up 4, and that's only up 3. Is that all right? Anything else? Sure? Okay, so far our parabolas, ellipses easier or harder than parabolas? About the same? More work? Okay. All right, I'll take that. Okay, a couple things we want to point out. If you want to look in your book on these pages right here, there's a whole bunch of formulas on there. If you want to go through and memorize either one of those, that's totally okay with me. Okay? If you understand the idea behind an ellipse, okay, the basic definition and how we use those foci and the major axis, minor axis, which one's bigger, which one's smaller, all that sort of stuff, it's going to help you understand and graph them more easily, and it's going to help you do hyperbolas. So if you do it the way I've shown you here, then you should be in good shape. Okay? All right, and we already talked about what a semi-major and a semi-minor axis was. Okay, go ahead and flip the page over. See how many of these we can get done. Let's look at that one right there. What's nice about this one? Okay, they give us the equation, the numbers are nice, and we haven't moved it anywhere, right? So what's the center? Center is 0, 0. So the center is 0, 0. So we've got that right there. Okay, now you'll notice that on this one, they put the y squared first. Okay, we can deal with that. It really doesn't make any difference if you're thinking about this the right way. You look at the y, look at the number underneath it, take the square root of that. How far are we going to go in the y direction? 3. 1, 2, 3. There's a vertex. 1, 2, 3. There's a vertex. Look at the x. Doesn't matter whether it comes first or second. Look at the x, look at the number underneath it, take the square root. Square root of 16 is 4, so we're going to go 4 units from the center in the x direction. So I'm going to be here and here. So this isn't a very oblong, okay, elongated, okay, sometimes they call it eccentric. This isn't a very eccentric parabola, or sorry, ellipse. Looks like this. Okay, it's a little better. These are all easy points to label, right? Okay, you can label those, no problem. Okay, now, I do need to mark where the foci are, and I need to label those. Those are always going to be on the major axis, so they're going to sit on the x-axis on this particular problem. How do we find out how from the center we go along the major axis to label the foci? Okay, it's big one minus small one. It's a squared minus b squared equals c squared. It's like the Pythagorean theorem, but we have to subtract so that we're inside. We have to make it smaller. This is a units in either direction. We're not going to go a units, we're going to go something less than that. Subtracting b squared helps me figure out what that is. So a is always the big one. So this is going to be 16 minus 9. That will equal c squared. So this is c squared equals 7. This is radical 7.
Wait, isn't it a squared?
Yeah, a squared. That's a squared.
Oh, okay.
Okay, remember this would be b squared on this one, and this would be a squared on that one. Okay.
Oh,
That number is, you don't have to square it to get that number. That number is a squared. You have to take the square root of it to get a. Okay. Any questions? Okay, can we do that? Square root of 7? Okay, Charles says it's approximately 2.6. I really don't believe Charles. Did you throw it in your calculator? Of course he did. Okay, it's a number it's bigger than 4 square, or square root of 4. It's less than the square root of 9. It's somewhere in between 2 and 3. So all you have to do is get it somewhere in between 2 and 3, anywhere in there, preferably somewhere in the middle or closer to 3. So I'm going to put a point here, and I'm going to put a point here. There are the foci, and then I just label them. Now, if I'm on the x-axis, the y-coordinate is 0. If I went forward from 0, 0 by radical 7, this would be radical 7, and what would this point over here be? Negative radical 7. It's that simple. Okay? Any questions? Easy enough? Okay. Could you do this one? Does it run horizontally or vertically? Major axis horizontal or major axis vertical? Horizontal, because the bigger one's underneath the x, right? Five units in the x. Only 2 units in the y. So this one is really elongated. Okay, you can label those points. Let's figure out where the foci are. Shelby, what do we think for that formula, a squared minus b squared? 25 minus 4. 25 minus 4 is going to be c squared. It's the big one minus the little one. That's going to be 21, so that means c is the square root of 21. Now, do you know exactly what that is? Okay, Charles says approximately 4.58, okay? The big deal would be that it's between the square root of 25 and the square root of 16. Square root of 16 would be 4, square root of 25 is 5. So they're really far out here, okay? I'm going to have a focus somewhere in between 4 and 5 here, and somewhere in between negative 4 and negative 5 there. This is going to be square root 21, comma 0, negative square root 21, comma 0. Any questions? Okay, let's take a look at this one right here. Oh, rats. I should have done these a little bit differently. Bigger?
Yeah, bigger's better.
Oh, the graph's bigger? Then it'd be like 2 sheets of paper. Which way is the major axis here?
It is vertical. No, it's still horizontal.
It's horizontal, isn't it? Because the bigger one's underneath the x. Okay, all of those are horizontal. I should switch this for next semester. Okay, where's the center? Careful. Okay, find the x, negative 1. Find the y, 2. So this is centered at negative 1, comma 2. So I'm going to go back 1 and up 2. Right there is the center. This tells me how far I'm going to go in the x direction. This tells me how far I'm going to go in the y direction. So how far in the x direction? 4. 1, 2, 3, 4. We're right here. Now, if this is the point -1, 2, and I slide over 4 units, that's going to put me at 3, 2. If I go over 4 units here, that's going to put me right here. That's going to be at -5, 2. All of those have exactly the same y coordinates, so they're all the same height above the x-axis. Okay, Susie, how far do I go in the y direction? Square root of 7. Okay, now square root of 7 is a pain in the butt. I bet Charles could approximate it. Oh, see. 2.64. It's in between 2 and 3. Since 7 is in between 4, which is a perfect square, and 9, which is a perfect square, it's got to be somewhere in between 2 and 3. So we're going to go up 2 point something. Okay, now, if I go up, which coordinate changes? The y coordinate changes. If I go up, it's going to change by radical 7. So this is at -1, 2 plus radical 7, and these should ring a bell. If I go down, I need to go down 1, 2, and a little bit more. That's going to put me about right there. The x coordinate is going to be the same, but this is going to be, I did 2 up radical 7. I'm going to do 2 down radical 7. This is going to be 2 minus radical 7. So notice how these kind of sound familiar. See how they're symmetric? 2 minus radical 7 and 2 plus radical 7. See how that symmetry always works out? It's similar to when we graphed parabolas. Put this little box around here to help me draw the right shape. And we're going to go from here around to there and like this. And then the only other thing I need is the foci. Shelby, again, what do I need here? 16 minus the 7. That's going to be c squared. Now, as ugly as these points were, look what happens here. This is a 9 equals c squared, so what is c? C is 3. So this means from this point, again, the major axis runs horizontally. I'm going to go 1, 2, 3. Right there's a focus. 1, 2, 3, and right there's a focus. So finding those points is pretty easy because they're right on nice grid lines. So if I go over 3, this is going to be 2, 2. And if I go back 3, this is going to be -4, 2. Okay? Got everything there, right? Any questions? Okay. All right, look what we've got left for Monday. We've got 6 graphs to do. Okay, I would like it if you got started. Okay, watch, don't go away yet. I would like it if you got started on the assignment and knew how to do these here. This one's pretty easy. Is this in a nice graph-friendly form? It's not, because that has to be a 1. We've got to have a perfect square with y and a number underneath, a perfect square with x and a number underneath, and this has to be a 1. How do I make that a 1? Divide by 8. So this is going to be y squared over 2 plus x squared over 8 equals 1. This one's a little bit on the ugly side. Where's the center? 0, 0. How far do we go in the y direction? Ooh, radical 2 is how far we go in the y direction. How far do we go in the x direction? Radical 8, which is a little less than 3. Okay? Take a look at this one right here. Okay, we'll do these on Monday. I just want you to watch. This is nowhere near a graph-friendly form. So guess what we're going to have to do here to make it look like this? A bunch of stuff. Each one of these has a perfect square in it. Does this have a perfect square in it? Okay, what's that word we use or that phrase we use? We're going to have to complete the square. Very good. Okay, please look that over. Know how to do the easy ones. Know how to graph them. We'll talk about how to set those up later. Okay? Have a great weekend.